Hi everyone, and in today's session I am now going to discuss about acidic nature of phenols. In the last session we discussed about the acidic nature of phenols as well as alcohols, and from that we came to know that alcohols and phenols both are acidic, but the acidic nature will be further affected by the presence of some other groups in the alcohols and phenols. But here in phenols, particularly I am discussing in case of phenols, phenols are acidic in nature. When they ionize, they will be giving us phenoxide ion and a proton. So this is what the phenoxide ion and proton. So again, the acidic strength of the given substance depends upon the conjugate base obtained by ionization. So this is giving in H plus ion by ionization means we should consider this as an acid. And acid upon losing a proton gives us a base which is simply known as conjugate base of this particular acid. So again, if the conjugate base is stable, then the acid will be more acidic. So acidic strength of the acid depends on the stability of conjugate base. More the stability of conjugate base, more will be the acidic strength. Then, let us check the stability of that conjugate base. This phenoxide ion, benzene with O minus, phenoxide ion is having 3 lone pairs on oxygen atom, and where any one lone pair among these can be withdrawn onto benzene ring, and that can involve in resonance structures. If this lone pair of electrons of oxygen shift between oxygen and carbon of benzene, then the pi electron density, a pi electron pair present on benzene. So because of conjugation between the lone pair of oxygen and the pi electron pair of benzene, the delocalization takes place. So by delocalization of that lone pair and pi electron pair of benzene, that will give us this kind of resonance structure. So here will be negative charge, right? And here the pi bond remains same and this pi bond remains same. The next structure, possible structure is this pi bonded electron. So lone pair of the negative charge means electron pair can move to this position, and that may lead to delocalization by one more structure. We'll be getting this kind of structure. Double bond O, right, with the 2 lone pairs, right. Then a pi bond here, and here is a minus charge. Here is a pi bond. In the next step, this pi bond, electron pair may move to this position, and parallelly this pi electron pair move to the next carbon. That may lead to the formation of one more resonance structure. So that is nothing but this one, double bond O with the 2 lone pairs, right? And here is a minus charge, and here is our pi bond, here is our pi bond. The next possible structure is that this negative charge means electron pair can move to this position, and as a result this pi bonded electrons again moving back onto the oxygen atom. So finally we will be getting this structure back to the original structure of phenoxide ion, right? And here is our pi bond, here is pi bond, here is a pi bond. So this phenoxide ion, which is conjugate base of phenol, phenoxide ion, is getting stabilized by these kind of resonance structures. So it is giving us almost 1, 2, 3, 4, 5. So 5 resonance structures. Phenoxide ion is getting stabilized by 5 resonance structures. So these 5 resonance structures makes that phenoxide ion more stable. So greater the stability of the conjugate base, as we discussed earlier, greater will be the acidic strength of the phenol. If we compare the acidic strength of alcohol with this phenol, so if you look at the structure of alcohols, I can take ethanol for example, CH3, CH2OH. If this one is ionized, we will be getting CH3, CH2O minus, the 3 lone pairs on oxygen atom, and H plus ion. So this ethoxide ion is obtained, and this ethoxide ion, let us check about this stabilization of this CB, conjugate base. So as we know that greater the stability of the conjugate base, alkoxide, greater will be the acidic strength. You can say this alcohol is acidic because it is capable of giving us H plus ion by ionization. But this conjugate base, to what extent it is stable? Let us check that. So if you look at this conjugate base structure, the oxygen linked carbon, the oxide ion present carbon, is having a methyl group on it. Basically, the alkyl groups, all the alkyl groups are electron donating type of groups. So they increases the electron density on carbon. See, in no way the oxygen electron density is decreased. So no group is present on the oxygen linked carbon. So that oxygen electron density is not withdrawn by any other group or the neighboring carbon. Instead, the electron density is increased on the carbon. As a result, so this electron density is not withdrawn by any other group on the neighboring carbon. So this alkyl groups are increasing the electron density, and this alkoxide ion is becoming less stable. There are no possibilities of stabilizing this Cb conjugate base, so that this Cb is less stable, and as a result this alcohol is less acidic when we compare with phenols. Phenols are more acidic. So phenols are more acidic, right? Alcohols are less acidic. That is due to the stability of the conjugate base. Greater the stability of the conjugate base, greater will be the acidic strength of its corresponding acid. So here the Cb, alkoxide ion, is being less stable. Its conjugate base being less stable, its corresponding acid will be less acidic in nature, right? So that's what about comparison between phenols and alcohols' acidic strengths, right? Now let us discuss about the acidic strength of phenols in presence of any other functional groups or substituents, how the acidic strength of phenols is affected. If we take a phenol is acidic than alcohols, it is known to us. But coming to the substitution case, if any substituent present on any other position of benzene along with the OH group, so how that group will impact the acidic strength of phenol. Say, we know that about electron donating groups and electron withdrawing groups. Electron donating groups, they decreases the electron density on benzene, and electron withdrawing groups electron withdrawing groups decreases the electron density on benzene, electron donating groups increases the electron density on benzene. Now, they will do this change, or they will cause this change by different mechanism. Let us take some examples here. Say I'm taking a nitro group here at ortho position of OH present carbon. This orthonitrophenol, I'm taking one more phenol, but this time the nitro group I'm taking here at meta position, meta nitrophenol, and then I'm discussing about para-nitrophenol, the nitro group present at para position. As we know that NO2 group is a strong electron withdrawing group, so that what happens, electron withdrawing action is shown by this group. So let us look into the resonance structures possible for this nitro group. See, OH, O will be having two lone pairs on the oxygen. Say if there is a NO2 group, say let us consider NO2 group at para position for better understanding. So if this involves in resonance structures, a lone pair of electrons of oxygen are withdrawn to benzene. As a result, the pi bonded electron pair here will move to the next carbon because it is in conjugation. So double bond O with one lone pair H. Why this happens? Because the NO2 group is pulling the lone pair of electrons, the pi bonded electrons between N and O away from the N. As a result, because of a conjugation between the pi electron pairs between the NO2 group and the pi electron pair of benzene, the pi electron pairs will participate in delocalization. And this will cause, as a result, what happens? So here it will be observing this N, single bond O with a minus charge, coordinate covalent bond with O, right? And then see, you can consider this pi bond is moving to this position. So what happens here? Double bond, here is a double bond, O with minus charge and this O with a plus charge. So this is causing this impact. So here the electron density is withdrawn towards the benzene because of presence of NO2 group at para position. And now the oxygen is experiencing electron deficiency, which may be rectified by pulling the OH sigma bonded electron pairs towards oxygen, and that will increase the acidic strength. So as a result, this hydrogen may be released easily as H plus ion. So presence of NO2 group is making phenol even more acidic. So that again relative position of NO2 group matters. So if NO2 group is present at ortho position, at meta position and at para position, in what way that will impact the acidic strength of phenol? So this NO2 group, if we look into the deep structure, detailed structure of this NO2 group, N double bond O, single bond O, O with a partial negative charge, N with a partial positive charge. Because of more electronegativity of oxygen, I can indicate like that. So O with a partial negative charge, hydrogen with partial positive charge. H and O are having partial positive charge and partial negative charge on oxygen. So they can have intermolecular hydrogen bond here. Due to this intermolecular hydrogen bond, the hydrogen cannot be released as H plus even though NO2 group is an electron withdrawing group, which causes more acidic strength to the phenol. So due to this intermolecular hydrogen bond, orthoisomer is not of strong acid. Looking into the meta isomer, at meta position, delocalization, that's what resonance structures possibility will not be there. It will not be there. So this NO2 group here will show only minus I effect, but not minus R effect. In this case, the NO2 group is causing minus R effect. By minus R effect, the electron density on benzene is decreased by NO2 group. As a result, the benzene is pulling the lone pair of electrons onto benzene. As a result, the oxygen is suffering from electron deficiency, which may be rectified by pulling away the OH sigma bonded electrons, and that causes increased acidic strength of the phenols. The case 2 is that here the NO2 group, even though it is present on benzene, here at meta position, the NO2 group cannot cause minus R effect. If you wanted to know that, you can draw the resonance structures by this. So it cannot undergo any resonance structures at meta position. It will cause just minus A effect. Here at para position, it will cause minus R effect. Generally, the impact or the significance of minus I effect is less than minus R effect. So the compounds or the groups in which where we can see minus R effect, their impact, the group's impact will be more on the acidic strength of the phenols. So phenols, although isomer is involving in minus R effect, as well para isomer also involving in minus R effect. So in case of meta isomer, minus R effect is not observed, instead minus I effect is shown. So here, looking into this, out of these three, which one will be stronger acid? If you go for that question, so let us label this, I can write this, para nitrophenol, considering that. So minus R effect causing groups, these two groups, mean the NO2 group at para position and NO2 group at ortho position are causing minus R effect. And due to intermolecular hydrogen bond, this ortho product or ortho isomer is not a stronger acid. That's the reason para isomer will be a stronger acid. So that para nitrophenol is stronger acid. And then next will be ortho nitrophenol, and least acidic strength will be for meta nitrophenol, in which the nitro group is causing just minus I effect. So that's the correct order of acidic strength of nitrophenols, ortho, para and meta nitrophenols.